I know that AI is taking up all of the oxygen in the room, but we need to be paying attention to the developments of in nuclear fusion. Fusion technology is the cleaner, more powerful counterpart of the very scary nuclear fission technology. And the rising tide that is caused by these developments of AI is actually going to assist the proliferation of nuclear fusion technology. I want you to pay particular attention to the developments happening in this article. I think it's actually kind of crazy. The biggest takeaway, if you don't want to take away anything else, if you want to close this video right now, the one thing you want to take away from this development is this is one of the few attempts where we're able to get more energy out of the nuclear fusion process than it was needed to get the fusion process started. We're going to get into why nuclear fusion is cleaner, why it is more viable, why it produces a lot more power, but yeah, let's see what the article has to offer. So this, by the way, laser-powered fusion. There's other ways to get the fusion process going, which we're also going to address in this article, but laser-powered fusion experiment more than doubles its power output. Let's dive into it. The world's only net positive fusion experiment has been steadily ramping up the amount of power it produces. So again, net positive fusion experiment. Why do we need to emphasize the fact net positive? Because it takes a lot of energy to get the fusion process started. And since this is very much in the experimental phase, most of the attempts have been needing more energy to just get the process going. In recent attempts, the team at the US Department of Energy's National Ignition Facility, NIF, increased the yield of the experiment first to 5.2 megajoules and then to 8.6 megajoules, according to a source with knowledge of the experiment. So, you know, these are tremendous numbers in terms of the energy produced, but the takeaway here is we're increasing the amount of energy that's coming out of this process. The new results are significant improvements over the historic experiment in 2022, which was the first controlled fusion reaction to generate more energy than it consumed. So again, a net positive fusion experiment is not happening for the very first time, but it's a very big milestone which makes the very lucrative fusion process feasible. Right? At the end of the day, if a process is creating more energy than is needed to get the process started, it's feasible. And this process is now almost, well, not almost, it's close to doubling the amount of energy output. The 2022 shot generated 3.15 megajoules, a small bump over the 205 megajoules that the lasers delivered to the BB-size fuel pellet. So the fuel pellet that is the feed for this nuclear fusion reaction is very tiny. Something to keep in mind, because when we're talking about other sources of energy, such as coal, gas, and basically fossil fuels, the energy feed is massive. This is much smaller than even compared to a tank of gas that just keeps your car running on the road. None of the shots to date have been effective enough to feed electrons back into the grid, let alone to offset the energy required to power the entire facility. The facility wasn't designed to do that. So the thing to keep in mind here, right, the National Ignition Facility, it seems that they're just running experiments. They just want to study if it's possible to get a net positive fusion result out of a process, and if the process is even possible. Had they had the capabilities to capture this energy and feed it back to the national grid, this could have been put to use almost immediately, but this is all very experimental. The first net positive shot, for example, required 300 megajoules to power the laser system alone, but they are continued proof that controlled nuclear fusion is more than hypothetical. The IF uses what is known as inertial confinement to produce fusion reactions. At the facility, fusion fuel is coated in diamond and then encased in a small gold cylinder called a Hohlraum. So, very tiny pellet, about the size of a BB pellet, but this has to be coated in diamond, and then it further encased in a gold cylinder called a Hohlraum. The tiny pellet is dropped into a spherical vacuum chamber 10 meters in diameter, which is, again, it is expensive to maintain a vacuum. Not only is preparing the feed expensive, you got to coat it in diamond, you got to wrap it in gold, and then you got to drop it in a massive vacuum chamber where 192 powerful lasers converge on the beam. Then you got to shoot this thing with 192, almost 200 laser beams targeted at this tiny target point, focal point. The cylinder is vaporized under the onslaught, emitting X-rays in the process that bombard the fuel pellet inside. The pellet diamond coating receives so much energy that it turns into an expanding plasma. This is crazy physics happening here. This is one of the hardest known materials. This is maybe the hardest known material, carbon-based diamond, and it receives so much energy due to the X-rays that are emitted from the fuel pellet that it becomes plasma. The diamond becomes plasma, which compresses the deuterium tritium fuel. And again, deuterium tritium are variations of hydrogen. And this is one of the things that makes fusion so lucrative. Sources of deuterium and tritium are ocean water, and we have that in troves. They're isotopes of hydrogen that is found in water. Anyway, compresses the deuterium tritium fuel inside to the point where their nuclei fuse, releasing energy in the process. So with fusion, you're trying to break nuclear material, radioactive atoms, but for fusion, you are fusing non-radioactive atoms together, namely hydrogen. The other main approach to fusion, magnetic confinement, uses powerful superconducting magnets to compress and contain plasma in a tight space, and space tight enough to create the conditions necessary for fusion. So at the end of the day, it seems like the goal for fusion technology is to um, create a pressure environment for deuterium and tritium so that they fuse. For the laser-based support, you basically coat it in a diamond pellet and a gold pellet, and then you fire a lot of lasers around it to get it to emit X-rays. And in that pressurized, and then when the plasma is created, that creates the pressure conditions needed to make the fusion happen. There's also magnetic confinement that creates this fusion. However, no magnetic confinement experiments have produced net positive results. Several are being constructed or designed with the exception that they'll hit that milestone. So far, the only net positive outcome where we're getting more energy out of the process than we're using to get the process started has only been seen from laser-powered fusion experiments. Let's take a deeper dive into fusion and why this is particularly lucrative, right? And we're using Perplexity to do some of our research and justify it. Nuclear fusion is a process in which two atomic nuclei merge to form a single, heavier nucleus, releasing a tremendous amount of energy in the process. This is the same reaction that powers the sun and other stars, where hydrogen nuclei are combined to form helium, emitting vast amounts of energy as a result. Literally powering the most powerful object known in our solar system, and we're trying to harness this on planet Earth. We are a crazy bunch of apes, guys. On Earth, the most efficient fusion reaction uses two isotopes of hydrogen. There we go, hydrogen, deuterium, and tritium, which fuse at extremely high temperatures over 100 million degrees Celsius. This is it. The 192 lasers, when they converge on the fuel pellet, it creates an atmosphere temperature so hot that it actually causes diamond to become plasma because of the very high temperature environment. So the temperature conditions needed to fuse these hydrogen isotopes are extremely high, and that is what causes that is what makes the initial conditions for fusion so expensive. And high-speed neutrons releasing energy. How does fusion compare to fission? Okay, fusion is all the rage, has been the technology that is being used currently and has been used to power like nuclear power plants. Nuclear fusion, by contrast, is the splitting of a heavy unstable nucleus, such as, again, unstable nucleus, right? So the feed material, what you start with, is already super radioactive. So it's very, very important to contain it, right? You have to have these massive reactor setups where these fuel rods need to continuously be shielded. So that they're not like killing people and animals and biological life around the facility. Unstable nucleus such as uranium-235 into two lighter nuclei, also releasing energy. Fission is the process currently used in all commercial nuclear power plants. If that changes, this is going to be a step function change in the abilities of what humanity is able to do if we're able to make fusion accessible for most commercial applications. All right, so differences, process, fusion combines, fusion splits energy output, more energy per mass than fission. This is incredible. Nuclear fission is already so amazing, so powerful, but fusion is able to produce more energy per unit mass than fission. Fuel, super abundant. This can be found in ocean water because it's pretty much heavy water, right? Deuterium and tritium, both stable isotopes of hydrogen. Uranium, plutonium, limited. That's the other thing. The fissile material, the raw material that sets off nuclear fission reactions, are also very limited. Not only are they very dangerous to handle, they're also very limited in quantity. So not super sustainable. Radioactive waste, minimal, short-lived, mostly helium. So again, like what happens inside the core of stars. Hydrogen fuses to form helium, and if there's any radioactive waste that's created, it's the half-life for that radioactive waste is very short, as opposed to the half-life of radioactive waste created from nuclear fission. So half-life basically is a measure of how quickly there is decay in radioactive materials, aka how quickly radioactive materials spontaneously become something that is safer and non-radioactive. So whenever you're done with nuclear fusion, you have to find a way to dispose of the end products, which are very, very radioactive and which will continue to be radioactive for very long periods of time. In fact, one of the challenges humanity faces with disposing of radioactive waste is if these radioactive materials are going to be waste products are going to be radioactive for centuries and centuries to come. If, for whatever reason, there is a cataclysmic event that wipes out humanity and humanity is re-emerging and they have to discover writing all over again. This is a valid concern, guys. It's crazy, but it's a valid concern. How do you mark radioactive waste from nuclear fission via symbols so that it is clear across whatever new cultures and whatever new languages may emerge that do not approach this material? It is dangerous. It will kill all forms of biological life. Now, with nuclear fusion, you don't need to worry about that because the radioactive waste products are going to become harmless within the span of, a single lifetime. Fusion again, no risk of meltdown. Reaction stops if disrupted. Risk of meltdown with nuclear fission. Chain reaction must be controlled. So with nuclear fission, we kick off a chain reaction. But with nuclear fusion, there's the risk of accidents is less because all you need to do is to continue to sustain the conditions of very high temperature that causes diamond to become plasma. If something happens and that process is disrupted, the fusion process just stops. The atoms stop combining. It's a very beautiful, natural, elegant safety plug, right? It's a very convenient safety tether. But with nuclear fusion, you have to continuously control the nuclear fission process because it's literally an uncontrolled chain reaction that you're extracting energy from. You need to, there's measures such as descending fuel rods into special containment units to try to contain chain reactions. And if that process goes wrong, then you can have a cataclysmic explosion. And we have seen a lot of nuclear incidents happen in the past, in the very recent past, and which is why there's a very negative stereotype with the use of nuclear technology. It's very clean, it's very green, but it's dangerous. People don't want it happening in their backyard. And here's the other one, no fissile materials used. So the stuff you use, the material, the raw material for nuclear fusion is not something that can be exploited for weapons technology because again, stuff that can be exploited for weapons technology needs to rely on nuclear chain reactions, right? But for fusion, the reason you can't weaponize it is the conditions to kick off the reaction are incredibly high energy. You can't weaponize that. So for these reasons, fusion is considered a much better alternative, right? Fusion fuel sources, deuterium from seawater, lithium and lithium for tritium breeding are plentiful and widely available, making fusion potentially inexhaustible energy source. This is truly going to be an infinite and clean energy source. Higher energy output. It just gives you a better yield for energy. Minimal radioactive waste, that's a big one. It's not safe before the process, during the process. It's extremely safe before the process, during the process, and after the process. Enhanced safety. Fusion reactors do not carry the risk of catastrophic meltdowns like Fukushima or Chernobyl, two events that are very, very scarring and fresh in our recent memory, collectively as humans. If the precise conditions for fusion are disrupted, the reactor simply stops within seconds. Again, just to generate enough heat and pressure to keep the fusion reaction going, you cannot weaponize that. And as soon as those conditions are taken out of play, the reaction stops. There's no risk. No carbon emissions, goes without saying. Low proliferation risk. Obviously, for all these reasons, nuclear fusion is much safer, much more productive, and much more sustainable than nuclear fusion. And for those of you who have just joined, I see two of you here. The reason I'm talking about this is we have made a stride in terms of making nuclear fusion a process that produces more energy than is needed to get the process started. So why should tech companies care right now? Because tech companies have been foaming at the mouth at at the developments they need to get a competitive edge over each other when it comes to AI. The one thing that is bottlenecking progress for AI is energy. It's pretty expensive to train models, to run inference, but companies and everybody else, everybody and their grandma wants to use AI. So tech companies are kind of scrambling to come up with energy sources that are sustainable. Well, to be honest, they don't really care about sustainable. They just care about something that's going to give them the tremendous energy output that they need. And nuclear fusion is the answer. Let's take a look at some of the initiatives that these tech companies have taken to resurrect nuclear energy from the grave, right? In March 2025, it's about like 3 months ago, tech giants including Amazon, Google, and Meta joined a cross-industry coalition to pledge support for tripling global nuclear capacity by 2025. Now, nuclear capacity is nuclear capacity, right? It doesn't matter if it's fusion or fission. If it's fission, we should be worried because it's unsafe. We're going to generate triple the amount of radioactive waste, and we're going to have to take care of how we dispose of this. But if fusion is used, this is going to be amazing. I think we can even beat these numbers by 2050. This initiative, coordinated by the World Nuclear Association, marks the first time major non-nuclear businesses have publicly backed a large-scale expansion of nuclear power. Direct investments and purchase agreements. Amazon invested over $1 billion in nuclear energy projects and technologies, including a substantial partnership with X Energy. Google, collaborating with Kairos Power to purchase energy from a fleet of SMRs, small modular reactors, with the first unit expected to be operational by 2030. That's coming up in 5 years. Again, I think there needs to be more investment in nuclear fusion technology because setting up this infrastructure, this isn't like a cloud service that you can spin up and down. This is hardware. This is heavy infrastructure. I think that tech companies should lean more towards investing in fusion projects so that all this infrastructure they're investing in setting up SMRs, which are you can't repurpose a nuclear fission facility to become a nuclear fusion facility, right? Um, so I hope there's more tech companies that are getting into setting up nuclear fusion facilities, seeking up to 4 gigawatts of nuclear generated power, and has issued requests for proposals for developers for large-scale nuclear power supply. That's Meta. Microsoft entered an agreement to purchase power from restarted reactor at 3 Mile Island, securing over 800 megawatts for its AI infrastructure. Microsoft is also working with Constellation Energy to revive and utilize existing nuclear assets. Okay, so tech companies are coming in droves to support the proliferation of nuclear technology. Tech companies don't necessarily, among them, have the expertise to distinguish what is good for the environment, nor do they care. What is going to be sustainable, nor do they care. They're in it for the short term. So I do hope that there is more awareness around how amazing nuclear fusion technology is. Um, and this clearly is the future. This is how we're going to be meeting our energy crisis. And this is how we're going to make energy shortages democratically met across the globe. Thank you for watching. We'll cover another piece of news soon. Yeah, till then.